Afternoon, everybody. I wanted to start taking you through and preparing you for chemistry paper 2. As discussed, I said I'd start to make some limb videos, and I thought I'd start with a nice and easy topic, which is the alkanes and alkenes. And in particular, it's looking at crude oil and how we process crude oil to make more useful products, and also how we take crude oil to make products such as alkenes. So essentially what we're going to do is just like we've been doing in class, we've been looking at a summary booklet, which you can download and print to use alongside this video. But what we're going to do today is we're going to take you through 4 key things around this topic. It is, as I call it, a green topic. So it is one of the topics that have been highlighted by the exam board, which is why we are taking the time now to go through it. If we go through it and there's still things that you're not sure on, then when you're back in lesson, please don't hesitate to ask, or you can email me with any questions and I can get back to you in regards to it. So we're going to start off with looking at what crude oil is, and then move on to hydrocarbons, and in particular the alkane family to start with. We'll look at the structure of the alkanes, and we also need to be able to describe the types of reactions that alkanes can undergo. We're then going to look at fractional distillation, which is a process that takes place to the crude oil, and then the types of products that are made from that process. We then move on to properties of hydrocarbons based on the size of the hydrocarbon chain, and you need to look at things like flammability, viscosity, boiling points, and we're going to talk a little bit about that. And then we get on to cracking and the process of cracking and what that generally entails. And then we look at the second hydrocarbon family, which are alkenes. And again, you need to be able to draw the structure of those and describe the reactions of them. So that's essentially how we're going to lay this out, and we're going to go through and start with what crude oil is. So normally in a classroom setting, we'd have a lot of Q&A, and obviously we can't really do this with a recording. So essentially it's going to be a lot of information. So that's why I said, please just email me with any questions you might have, or if you're unsure of something. So we're going to start off with crude oil. So you'll already know a little bit about crude oil. So you'll know, for example, that it is a fossil fuel that has been made over millions of years. So, for example, dead plankton may have, or organisms have died. Their bodies have settled on the sea floor. They've then been covered by sediment, and over millions of years, they've been compressed and formed a fossil fuel. And that fossil fuel is crude oil. So when we're talking about crude oil in this context, we're talking about crude oil as a mixture, and I'm going to underline that, of hydrocarbon chains. So when I'm saying a mixture, I'm underlining that word because you need to know the fact that it is a mixture, and we can separate it out by using fractional distillation, which we're going to talk through the process of. I've introduced the word hydrocarbon. Believe it or not, I've seen exam questions asking you to define what a hydrocarbon is. So just to make you aware, it's a molecule that contains hydrogen and carbon only. Okay, so if it's got oxygen in there, then it's not a hydrocarbon. So it's a molecule that contains hydrogen and carbon only. So a crude oil, we would normally extract from the ground. We'd dig it up through the ground, from the ground, and then we would process that. It's a mixture of hydrocarbon chains, and I want to make clear that are of different lengths. So we have different hydrocarbon chain sizes. So they range in size from maybe 2 or 3 carbon long to hundreds of carbons in length. So you just need to be aware that they're the key things around what crude oil actually is. Now, it's a mixture of hydrocarbons, and the first kind of hydrocarbon family that you'd have been taught in the lesson is our alkane hydrocarbon family. So we're going to put a little heading, alkane. Now, for your GCSE in both higher and foundation tier, you are expected to be able to draw the alkanes, at least the first four. You're also expected to be able to describe their structure and a little bit about their reactions as well. Now, their name, I'm going to give you some hints and tips here. So the name actually helps you to think about its structure. Can you see how it's got one E? Okay, now this is going to sound really stupid, but the fact that it's got one E tells us that actually it has a single carbon to carbon bond. Okay, so when we come to look at alkenes, they've got two E's and they've got double bonds. So we'll talk a little bit more about that when it comes to alkenes. But alkanes have got one E, which means they've got a single carbon to carbon bond. Now, we should remember from when we looked at the periodic table that carbon is in group 4 of the periodic table, which means it can form 4 bonds. As you can see, we're talking about hydrocarbons that are molecules made up of just hydrogen and carbon only. So these are both non-metals. So we could say that actually alkanes are covalent molecules, simple covalent molecules, because they're non-metals. And as such, they're sharing electrons when they form their bonds. And because carbon is in group 4 of the periodic table, that means that carbon should form 4 bonds. So that means in our drawings of carbon, hydrocarbons, that every single carbon should have 4 lines coming from it. So when I look at methane, I know it's methane. I know its formula is CH4. And because it's got 1 carbon, it means it's actually got 4 hydrogens attached to it. And we would draw it like that. So if I count all the lines, 1, 2, 3, 4, I can see that carbon has formed 4 bonds. And that's what I'd expect it to form. Now, how did I work out that for 1 carbon, I'd have 4 hydrogens? Well, there is a general formula to our alkanes, and this is something that you need to be familiar with. So we call this our general formula. So a general formula is what we can use to predict the structure of an alkane or an alkene. So we do cover general formula again when we look at alkenes. So this is a general formula for an alkane. So it is CnH2n plus 2. So if I know my carbon number, I can then work out what my hydrogen number should be based on this general formula. So as you can see, here I've got 2 carbons. So if my N was in fact 2, that would mean my hydrogen number would be 2 times 2 plus 2. So as you can see, that's quite easy to work out. So that's going to give me a formula of C2H6. So it's a good way of allowing you to then be able to draw the structure. So because I know the hydrogen number is double add 2, I can essentially work out that that there is an alkane. And on a foundation tier paper, I've seen it where they give you different molecules names or formulas, sorry, and you've then got to be able to spot the alkane. So alkanes are double plus 2. So hopefully you feel confident at being able to draw those. So as you can see, I've given you the first 3. So you can have a go at drawing butane, which is the next one in the load. So we've got essentially 4 carbons. So what I'd suggest to do is pause the video and give that a go, and then we'll go through it. Okay, so hopefully you've been able to do that. So let's have a little look. I'm going to use my general formula to predict the amount of hydrogens. I know that if my carbon number is 4, I would do 4 times 2 and then add 2 onto that. So that would give me a hydrogen number of 10. So following the rules, which is that each carbon has to have 4 lines or 4 bonds, I can see quite easily that I've got my 4 carbons laid out like that. I know it's an alkane, so it's single bond carbons, remember, 1E. And then I make sure each carbon has 4 lines. So 1, 2, 3, 4, that one's happy. 1, 2, 3, 4, yep. Same again. And then I put my hydrogens on afterwards. So hopefully that helps you to be able to draw the structure of alkanes. And our alkanes are in here. It's a mixture of hydrocarbons that's inside our crude oil. So we want to be able to actually get these products out because these are really useful products. We can use them for things like fuels or lubricants, and we need to be able to take our crude oil mixture and extract these different size chain hydrocarbons, and we're going to go through the process of fractional distillation now. So hopefully you found that useful. So here is our typical picture or typical diagram of the fractional distillation chamber. You do need to be able to describe what is going on. I have seen this come up as a sort of 4 or 5 mark question on a higher tier paper where you're actually describing the whole process and the outcome of it. It's not very clear, but I'm hoping you can see that there's different temperatures on the scale here, and I will put it on the side just to help you out because it's not very clear. It's not photocopied very well. But essentially, fractional distillation is how we process crude oil into making more useful products that we can then utilise and use for different things. So we're going to basically go through the process of what happens inside the distillation chamber. And then we're going to talk a little bit about the useful products that can come out of it. So here is crude oil. We know that crude oil is a mixture of different size chain hydrocarbons. We also know that it is a liquid. And if we heat a liquid up, so as you can see in the picture, we're going to basically pump through our crude oil into a heater. And what that will then do as you heat a liquid, the liquid is going to turn into a gas. Okay, so the heater in the furnace is essentially used to turn our crude oil liquid into a gas. So depending on the size of the hydrocarbon chain, that will decide really what the boiling point of that molecule is. Because smaller chains have a lower boiling point. So when I'm taking my mixture of crude oil, my smaller chains are going to in fact boil first because they require less energy to break the bonds and as such, to break the intermolecular forces, and as such we can separate them out a lot easier. So we heat up our crude oil mixture, our smaller chains are going to boil off first, and they will then enter the fractional distillation chamber. Now, just a couple of things about the chamber. It has got a temperature gradient to it. Here it is generally cooler. Okay, so a cooler temperature, as you can see, 20 degrees Celsius. And at the bottom of the chamber, we are generally hotter. So as you can see, there's a temperature gradient going on. Now, we've just said that our smaller chains have a lower boiling point. So they're going to boil first. And as if they're a gas, they're still going to be a gas at 300 degrees and 200 degrees and 150 degrees. So they, therefore, are going to travel they're going to travel up to the highest part of the chamber. Can you see how you've then got these little things here? Now, as you can see, the temperature is gradually getting colder. So that gas is eventually going to condense back into a liquid. And as such, the liquid will then form around about here. And we can then siphon it off and take our products. Okay. So the temperature gradient actually is a way of allowing us to condense the different size chains at different temperatures and then extract them. So it's quite a clever process, really. So where do we generally find the different size chains? So we generally find our smaller chain hydrocarbons at the top of the chamber because they boil first and they will still be a gas at the higher temperatures, which is why they'll progress up through the chamber. But at the cooler temperatures, it will begin to condense and we can then extract it as a liquid form. Our larger chains or longer chain hydrocarbons, you generally will find at the bottom of the chamber, because again, they will require a lot more energy. So larger chains or longer chains, have a higher boiling point. Again, you've got more bonds going on there, so therefore more energy would be required. So they would actually turn back into a liquid at a higher temperature. And that's why you generally find your longer chain molecules at the bottom of the column. So I've seen on both higher and foundation tier papers, you need to be able to essentially describe the processes that are going on. Dodgy camera there. And where we would find each size chain. Now, these products all have different uses. So as you can see, petrol, diesel, we can use them for things like transport. We also use them in petrochemical industry as what we call feedstock. So essentially it's the things that we need to make other molecules or products. So for example, we might use this, we do use this for making polymers. So we talk a little bit about cracking, which is a process that takes place to our long chain hydrocarbons. We turn them into alkenes, which can then be used to make polymers. We can use them for other things like solvents, detergents. So these products here, once separated out from the crude oil, actually go on to make more and very useful products as well. So let's move on then. So we're going to actually look at the properties of hydrocarbon chains depending on their size. You need to be able to, for example, interpret data on these factors. Again, you might have to be able to talk about the properties in relation to the fractional distillation chamber. So higher boiling points, longer chains, lower in the chamber. Thicker viscous substances are generally longer chains. So you might have to link this to the fractional distillation column. So we'll go through this. So when I'm talking about a short chain, what I'm talking about is carbon 2, sorry. It varies. So up to carbon 25 or something like that. And then carbon 50, 25 up to carbon, 35. It's just to show you that the carbon chains are getting bigger. So I'm going to go through just the overall. So shorter chains, overall, their properties are this. Longer chains, overall, the properties are that. You might have a range of different size chains and then have to put their properties to that. Just remember that the principle is the same. So don't worry too much about that. So short chain hydrocarbons, we've already said from the fractional distillation chamber, they have a low boiling point. Longer chain hydrocarbons have a high boiling point. Viscosity is the thickness of the liquid, so how gloopy it is. Shorter chains are less viscous, so runny, and longer chains are generally what we call thick and gloopy. Hopefully I'm spelling gloopy correct. So they're thick and gloopy. So think of things like syrup. Syrups are really thick and gloopy liquids. So longer chain hydrocarbons are the same. Same with things like tar and what they use to make the roads. That's a very thick and gloopy substance. So that's how you describe the viscosity of a long chain hydrocarbons. Now, the shorter chains are generally lighter in colour. Some are clear, some are a lighter yellowy colour, but they're generally lighter in colour, which means our longer chains are darker, and they can vary to really dark colours of yellow, for example. And flammability is how easily it catches fire. So our shorter chains are very flammable, and our longer chains are less flammable. Okay, so you might be given a set of data where you've got a table with different size chain hydrocarbons, and then you've got to sort out the properties. So knowing the general pattern for shorter chains and longer chains, you can then work that out. Now I'm going to come back to complete and incomplete combustion because it does tie into alkenes. So I want to talk to you about how we make our alkene molecules. As I've said in the fractional distillation process, a lot of this process is about making the materials that's required to go on to make polymers. So we're going to talk essentially how we take our long chain hydrocarbons and make them into more useful products, such as the monomers required to make plastics or polymers. So we're going to go through the process of cracking, and I want to show you some diagrams here because often you're given this kind of diagram here, where you've got to really think about the processes that's going on. I've also got a diagram to show what's happening to the molecules, because cracking essentially is taking a long chain hydrocarbon, an alkane in this case, and breaking it into smaller chains, more useful chains, may I add. So as you can see here, I've got an alkene being formed here and a smaller alkane, which could then, for example, be used as a fuel for transport. So let's just go through the key things around this. So cracking, by a definition, is basically splitting a long chain hydrocarbon into smaller useful products. And there's a couple of things that are required for that to happen, one of them being a catalyst. So we're going to talk about catalyst to start with, because catalyst does come up in the rate of reaction topic. It also comes up when we're talking about reaction profiles and how catalysts lower the activation energy. So catalysts, as you will remember, speed up reactions by lowering the activation energy, which is the energy required for the reaction to take place. So in this case, my porcelain chips act as a catalyst, and essentially I'm taking my long chain hydrocarbon, applying heat to it with a catalyst, and what it then does is it breaks that long chain into smaller, more useful products, which in this case is a gas, which I could then collect and then use as desired. Sometimes the catalyst might be aluminium oxide, powdered aluminium oxide, again to speed up the reaction. So just be aware that aluminium oxide can also be used as a catalyst for the cracking process. Now, the reaction is what we call a thermal decomposition reaction. Now, thermal, we should know already, is to do with heat. Decomposition means to break down. So essentially, I'm taking heat and I'm breaking down my long chain into a smaller chain. So I'm not reacting two reactants together. I'm taking one reactant and I'm breaking it up. So that, again, I've seen that asked where you've got to define what that means or recognize that the cracking process is a thermal decomposition reaction. So you need to be mindful that you're aware of that. So it's a thermal decomposition reaction. We're taking a long chain hydrocarbon, we're cracking it. So this, for example, could be aluminium oxide powder. And as you can see, this is an example of catalytic cracking. There's actually two processes of cracking that you need to be aware of. One is a catalytic cracking and the other is steam cracking. And as you can see, catalytic has got our catalyst, which in this case is aluminium oxide, powdered aluminium oxide. And what essentially it does is it splits the molecule apart, the long chain hydrocarbon, on the surface of the catalyst. And that's why it's called catalytic cracking. It actually does that process on the surface of the catalyst. And as you can see, I've broken that down into two molecules here, ethene and another alkane. What I do want to point out is that, can you see how actually the number of carbon chain hasn't changed and the number of hydrogens hasn't changed as well? Sometimes you're asked to draw the missing product from the long chain hydrocarbon. So it's all got to add up to what the original hydrocarbon chain was. So just be mindful of that. Steam cracking essentially is what it is. We're using steam, which is obviously vaporized water, to break apart the long chain hydrocarbon. So essentially we are taking a long chain hydrocarbon plus steam and very high temperatures to break apart the chain. Again, the process is essentially the same. Our long chain becomes smaller, more useful products. Okay, so that is the process of cracking. So now we've got our alkene. Okay, so this is an alkene. I know that because it's got a double bond, which actually is a very useful product in polymerization, which is the formation of a polymer, plastic. So we're going to look at this family now, and essentially being able to draw the structure of an alkene and talk a little bit about its structure. And that's what we're going to move on to look at now. So we've got our alkenes. You'll be glad to hear on the last page of the booklet. We're going to look at alkenes. So as I said with the alkanes, the name helps you work out what it is about. So can you see how I've got double E in the name? So that should be a little hint to say that is a double bond. Okay, so it's a double bond carbon. And for GCSE, you need to know that there's only one double bond carbon in the molecule. So you can see you've got your 4 alkenes that you need to be able to draw here. And what I need to really point out to you is if I'm being asked to, for example, draw butene, I would always put my first carbon as my double bonds and then my other carbons as my single bonds, just to help me. Then the rules are the same. We want to make sure each carbon has 4 bonds, 4 lines therefore. So 1, 2, 3, 4. 1, 2, 3, so it just needs 1 more. 1, 2, so it needs 2 more. 1, so it needs 3 more. So that way you can work it out in terms of drawing the structures. You will be expected to be able to do that. Just like the alkanes, there is a general formula. Okay, so this time the general formula is CnH2n. So in other words, if I know my carbon number, my hydrogen number is just double. Again, double E, double the hydrogen. That's another way of remembering that. So if I've got 10 carbons and it's an alkene, then my hydrogen number would be double that. So it would be 20 in this case. Now, a couple of things that you need to be aware of in regards to alkenes is that we call them unsaturated molecules. And that's got to do with the double bond. Essentially, it makes it more able to react, and we then can actually use a specific test to identify alkenes, and that is the reaction of alkenes with bromine water, which is the last part of the page. So we're going to look at the reactions of alkanes and alkenes with bromine water. And what we're going to essentially do is we need to be able to describe the reaction that's actually going on. So I'm going to draw the reactions above it just to help explain what's actually happening. You are expected to know the results of this experiment and describe how to do this. So we're going to start off with an alkane. So our alkane, we know already, is a carbon-to-carbon single bond. We call that a saturated carbon bonds. So that makes it quite difficult to react, which is why actually you can see that my alkane doesn't react with bromine water. I'll talk a little bit more about that in a sec. My alkene, double E's, got my double bond, and we call that unsaturated. And bromine water is made up of bromine. Okay, and the colour of bromine water is orange. And again, you need to know that. So I've got my alkane molecule, but we might not know what these molecules are. We've got to test to see if they're an alkane or an alkene by reacting with bromine water. So because the alkene's got a double bond and is unsaturated, that makes it more likely to undergo what we call an addition reaction. In other words, I'm adding the bromine to the molecule. Here, we've got our single carbon-to-carbon bond. That's not going to be able to do that. So when we look at the results of the experiment, can you see how actually the alkane will stay orange in colour? It's obviously in black and white, so we've not got a photocopied colour here. But can you see how the alkene actually changes the colour of it? It has reacted with the bromine. Now, we actually call this decolorizes the bromine water. So alkenes decolorize bromine water, so it basically makes it go clear, changes it from an orange to a clear colour. And there's a reason why that happens. So if I have, for example, ethane, okay, which is a single carbon-to-carbon bond, and I have ethene, okay, double bond. So here's my alkene, here's my alkane, and I react that with bromine. Can you see how actually it's going to be very difficult for that bromine to join on to this molecule here because of the single carbon-to-carbon bond? But this one here has a double bond. It is what we call unsaturated. So actually it can undergo an addition reaction by breaking that double bond. And the bromine then adds onto the alkene. And as a result of that, we get a decolorizing of the bromine water. Now, you need to be able to describe that reaction. You're very rarely asked to, well, I've never seen it being asked where you've got to draw what's going on. But I just think drawing it helps break down why it changes the colour of the bromine water. Now, the last thing we need to look at is how these two molecules undergo combustion reactions. So we're going to go back through to the booklet to where it says complete and incomplete combustion. So complete combustion, just to summarise what these two words actually mean. So complete means plenty of oxygen. Usually that's what that means. And incomplete usually means there's less oxygen. Now, you also get different products formed in a complete and incomplete combustion. Just to make you aware, combustion is what we call burning. And we're going to start off by looking at complete combustion to begin with. So complete combustion is when we've got a plentiful supply of oxygen. And if I take the reaction, for example, of methane plus oxygen, the two products I would make are carbon dioxide and water. And you need to be able to say that you will make carbon dioxide and water when you undergo complete combustion. Now, this obviously isn't balanced, so I'd want to balance this equation by doing that. So you might, for example, be asked to balance the equation. Again, remember, it's about counting up the atoms on each side and making sure they are equal on each side of the arrow. And we have practiced that. Incomplete combustion, you make something different. So we've just said that incomplete combustion is when you don't have as much oxygen present. Alkenes usually undergo incomplete combustion. So for example, if I had an alkene of C4H8, again, double the hydrogen, that's how I know it's an alkene, plus oxygen, okay. Can you see how I've now got a new product in this reaction? Don't worry about the balancing of the equation. I'm just wanting to show the fact that I've made another product here, which is carbon monoxide. And carbon monoxide is a product of incomplete combustion. And you may go on to know a little bit more about that. So, for example, it's toxic. It can basically stop red blood cells from carrying oxygen. Now, in incomplete combustion, you generally get a smoky yellow flame. And that's how you know it is, in fact, incomplete combustion from an experiment point of view. So just wanted to obviously give you an idea of some of the reactions of an alkane or alkene, but hopefully that's given you an insight into, or a recap over, should I say, of what you have covered in lesson. And again, like I said at the start, if there's any questions or you're not sure on something, please don't hesitate to give me an email or ask me next time I see you in class. All right, thanks guys. Bye.